Hello everyone, myself Mansi Bhanware and I will be starting with the presentation of our group whose topic is multiple expansions of electromagnetic fields. Now first, what is multiple expansion? In simple terms, we get the fields at distant points which are given in terms of sources in small region. This is the system and here we can see there is a charge distribution and we can define the fields due to this small region at a distance r. Now, for the field at distance r due to the arbitrary charge distribution can be defined by the Coulomb potential, which whose equation is this. And for this condition, that is r being much greater than r dash, we get the final expansion expression as this, which can also be written as this. Now, multiple expansion of the electromagnetic fields, which is the main topic of our discussion. Here are the Maxwell equations in a source-free region of empty space with the time dependence of e raised to power minus omega t. Now, if we solve equation 1 and 2, if we are eliminating e, we get these three equations, and if we are eliminating h, we get these three equations by solving equation 1 and 2. Now, in equation 3 and 4, the Cartesian components of E and H satisfies the Helmholtz wave equation, which is this, and each such component can be written as an expansion of the general form like this. And then we can define the multiple field equation. But it becomes really complicated. So we will follow a different and easier path to find a pure multiple field of order L, N. Let's first define a magnetic multipole field with the following conditions. Now, in this expression, this is the radial function, and from the equation number 4, we get this expression, and combining equation number 6 with this equation, we get this equation number 7. Now, the electric field of the magnetic multipole should and must satisfy the equation number 7. From equation 7, if we want to determine purely transverse electric field, there are two things we should consider. We should keep in mind. First is if we notice that L acts only on the angular variables, that is radial dependence of E must be given by this function. Now, second thing is L when acts on the epsilon Lm function. It transforms the m, but the value of L remains unchanged, which concludes to the fact that E can be linear combinations of epsilon with different m values and a common L value with equation 7. Also, the components of E should compensate for the fact that the m is changing because of L. Now, this discussion gives us the equation for the electric field like this. Now, this is equation number 8 along with equation number 4 gives us the electromagnetic fields of magnetic multipole. Now, magnetic multipoles are also called as transverse electric multipole because, as we can see in the equation 8, the electric field is transverse to the radius vector. Similarly, the fields of an electric field or transverse magnetic multipole, similarly the fields of an electric multipole or we can call it as transverse magnetic multipole of order L, M can be specified by this condition. And from here we get the electric multipole field as equation number 10 together with equation number 3. Now these two sets of multipole field equations, that is equation number 10, that is this set and this set, can be shown to form a complete set of vector solutions to the Maxwell equations in a source-free region. And by combining these two fields, we can write this general solution to Maxwell equation where this term is the normalized form, and AML, M and AEL, M can be calculated from these two expressions. Here AEL, M and AML, M specify the amounts of electric and magnetic multiple fields and can be determined by the sources and the boundary conditions. equations. Coming to the next topic, properties of multipole fields, energy and angular momentum of multipole radiation. First, taking the first condition, Kr being very less than 1, which is called as the near zone. From here, we can see this function being proportional, that is the radial function being proportional to NL, which is given by this. Now, the limiting behavior of the magnetic field for an electric multipole is given by this, which eventually leads us to this equation. Now, this is an important operator identity, which if we apply it on this expression, we can notice that HLM is smaller in magnitude than ELM by Z0 by a factor of Kr, which ultimately gives us the conclusion that in near zone, magnetic field of electric multiple pole is always going to be less than electric field of the electric multipole. For magnetic multipole fields, E and H can be interchanged, like as shown here. Now coming to the second condition, that is Kr being much greater than 1, which is called as far or radiation zone. The multipole fields depends on the boundary conditions that are being imposed. Let's take an example of outgoing waves. The radial function is proportional to the spherical Hankel function, which is this, and here we are using the asymptotic form of the spherical Hankel function. Now, in the radiation zone, we get the magnetic field for electric multipole like this, which eventually gives us this. But applying this condition, we have the final expression of electric field like this, where n is the unit vector in radial direction. Now, for magnetic multipoles, the same relation holds because the Poynting vector is directed radially outwards for both types of the multipole. So, the multiple fields of a radiating source can be used to calculate the energy as well as angular momentum carried off by the radiation. Let's consider a linear superposition of electric multipoles with different M but L. For harmonically varying fields, the time averaged energy density is given by this expression, and in a spherical shell between R and R plus dr for Kr much greater than 1, we have the following an expression for the energy. And if we are going to calculate in the general form, we need to do these replacements and the total energy becomes the incoherent sum over all the multiples. So also we know that the time average momentum density is given by this expression, which leads us to this expression. The x and y Cartesian components of dm by dr, that is mx and my, vanishes for a simple m value, and dmz by dr is equals to m omega by du by dr. From here we can do a obvious quantum interpretation, and that is the radiation from a multipole of order L, M carries of mh bar units of z component of angular momentum per photon of energy h bar mu. Classical result of the ratio of square of angular momentum to the square of the energy for a pure L, M multipole is given like this. But in case of the quantum mechanics, these substitutions are made, like for in place of mz square, we have to consider the x and the y components as well, and the m square is replaced by L into m plus 1. Now for L, M multipole field containing n number of photons which satisfies both the limiting cases, that is the quantum and the classical, we get this expression. So the quantum mechanical interpretation of the radiated angular momentum per photon for multiple fields contains the selection rules for multiple transitions between quantum states. Let's say we have two states, J, M and J dash, M dash. So the possible multiple transitions have L, M such that the J minus J dash mod of J minus J dash is less than L, which is again less than J plus J dash, and the value of M becomes capital M minus m dash. Now it is also necessary to state the sorry. It is also necessary to state whether the parities of the initial and the final states are the same or different. The parity of the initial state can be calculated by the uh, not, is equal to the product of the parities of the final state and the multipole fluid. We know that the parity of epsilon is minus 1 raised to power L, and thus which gives us the parity for electric multipole as minus 1 raised to power L and magnetic multipole as minus 1 raised to power L plus 1. So if the parities of the two states are same, we see that parity conservation restricts the possibilities so that only magnetic dipole and electric quadrupole transitions occur. If the states differ in parity, then electric dipole and magnetic quadrupole radiation can be emitted or absorbed. So now we will moving on further with the presentation. I would like to hand over to the next person. Thank you.
So, moving on with the angular distribution of multipole radiation. For a localized source distribution, the fields in radiation zone can be represented by these two equations, where the coefficients Am of Lm and Ae of Lm will be discussed later. So, the time average power radiated per unit solid angle is given by this equation: dp by d omega is equal to same z naught over 2 k square into a mod square, where xlm is basically a normalized way of writing L dot ylm. The electric and magnetic multipoles have same angular dependence, but their polarizations are at right angles, basically perpendicular to each other. So the multipole order can be determined by the measurement of the angular distribution of the radiative power, but in order to determine the character of the radiation, we'll have to use the polarization measurement. For a pure multipole of order L, n, the angular distribution is reduced to this equation. Uh, Further on, using the properties of XLM and the property of L dot y for different cases of L plus and L minus, we can further expand this equation to this form. Uh, and also using the sum rule for the spherical harmonic function as it follows it, so x will also follow it, and so its summation over m minus L12 will give us 2L plus 1 over 4 pi. So this tells us that the radiation distribution will be isotropic from a source that consists of a set of multipoles of order L, and it will be independent of m. Uh, so on integration of uh, dp by d omega over all angles, we'll get the total power radiated as a function of the coefficient a in this form. But this is only for a pure multipole. For a general source, the angular distribution is given by this equation, which on integrating over set of all angles is reduced to this form, where it depends on both A and AM coefficients. This shows that the power radiated is just incoherent sum of contributions from the different multipoles. Now, using the simplified forms of power radiated per unit solid angle, which is this one, uh, we'll be seeing the plots of the dipole and quadrupole radiation pattern for different values of L and M. So like so using that dp by d omega equation and substituting the value of y of ylm in it, uh, we'll get the for L equal to 1 and M is equal to 0, we'll get this equation where basically x is nothing but cos of theta, So on substituting that, this equation will be further simplified to 3 over 8 pi of sine square theta, and upon plotting this, we'll get this dipole radiation pattern for L equal to 1 and M is equal to 0. Similarly, for L equal to 1 and M equal to plus minus 1, we'll get this kind of equation, again substituting x equal to cos theta. This will be simplified to this equation, which when plotted will give this radiation pattern for L equal to 1 and M equal to plus minus 1. Then next plot is for L equal to 2 and M equal to 0. So this is the equation that we'll get on solving the dp by d omega equation, which simplifies to 15 over 8 by sine square theta cos square theta. And the radiation plots look something like this. Then moving on to L2 and M1 plus minus 1 case, this will uh, this will give us substituting in dp by d omega equation, will get this equation of this form, which again when substituted with x equal to cos theta will reduce to 5 over 16 pi into 1 minus 3 cos square theta plus 4 cos 4 theta. Uh, Upon plotting it, we'll get the radiation pattern, which will look something like this. Then for again L equal to 2 and M equal to plus minus 2 case, we'll get the solution of this form, which is further simplified to 5 over 16 pi into 1 minus cos 4 of theta. Uh, the radiation pattern for this case looks something like this. So that's all about the plots. Now handing over to Vignesh.
Hi, so I will be presenting this part for sources of multiple radiation in multiple moments. Since we have already discussed multiple radiation, we now move on to the sources that generate them. Here we have assumed a charge density, uh, current density, and intrinsic magnetization to be well behaved, and this follow this distribution. And we have these basic Maxwell equations for E and H dash, where H dash is given by V by mu naught. And we can further translate these equations into Helmholtz wave equation, where del square plus k square to h bar gives you the curl of J plus curl of magnetization. And we also will use the continuity equation, and E dash is given by E plus I by omega send lot into J. So to find the multiple coefficients, we need r dot h dash and r dot e dash, as we will see forward. And we can use this property of r dot curl of A can give you I L dot A, where L is the angular momentum and A is any vector. So in this, we can multiply R. We can take dot product with R, both sides, and the RHS will give. We can assume this to be A, and then the RHS will give us I L dot this A that we have assumed. Similarly for the second part also. And then later on, we can find this R dot H dash dot product by integrating uh, using Fourier components. And similarly for R dot E dash, as we have discussed, the multiple coefficients can be given by this function where YLM is the spherical harmonic function and G and L are functions of KR. And we will also use this three equations to find the boundary conditions. So in requirement for the outgoing waves, infinity makes this AL2 term to be 0, and we are left with only this term and this term. So these all will be equated and they all become equal. And then to find the further find this value, we also need to replace e to the power ik x minus x prime by x minus x prime. To do that, we will use the spherical wave projections from the spherical harmonic function, where we can use this property of spherical harmonic function multiplied by e to the power k x minus x prime by x minus x prime will give us this value, and then we can take the Fourier components of these individual parts to find the value of e to the power I k x minus x prime for a particular x prime. And then so this value for this would be given by this integration, and then we can replace that value here with this. These are the Bessel functions, and these are the above parts which we have already found. This r dot h is replaced by this part, and this part is replaced by the integration of this part right here. Similarly, for the am coefficient also. Now, to further simplify these equations, we can use these following identities. And we see that if we replace a by m in this first equation, we can like find this curl dot and curl of j can be written as this L dot a, where a is the a is written as j. So here we have written that part, and for the so this in this part for the first term we have like used the continuity equation, and for the second term we have used the Green theorem, where we have like basically we have converted this part dot j, and then for the radial integration by parts on the third term. So simplifying all, we can like calculate the multipole coefficient for the electric multipole, and similarly for the magnetic multipole we can find the value by doing the same process as above. So we have simplified the multiple coefficients, and now in the real physics field, the source dimensions are very small compared to wavelength. So for such terms, we will use only the small terms for KR. And when we do that, we see that the multiple coefficients comes up to be this and this right here. And individually, the coefficients can be written as the superimposition for the two multiple moments induced, and this one is induced due to magnetization in the case of electric multipole. And here we find that the magnetic multipole can also be written as this term, where we have assumed kr to be very small, and we have made assumption for the Bessel functions, reducing the coefficients to this form. Yeah, so that's it for this part. We will use these coefficients later on in this part. So, so the next topic is the multiple radiation in atoms and nuclei. The transition probability for the emission of a photon is given by the energy h nu, for energy h nu given by the radiated power divided by the energy, and the power we have calculated before here in the angular distribution was this. So we can use this power to find the transmission probability, and then this mod of a square is given by mod am square plus a square. So this transmission probability can be written as this power divided by the power h nu, and we write it in this form where we have taken QLM plus QLM prime to be equal to 1 by C VM LM plus MLM prime. You can see it from here that this QLM, when you add this two term, this will give you 1 by C times this QLM terms. Now to have an estimate for effective magnetization, we will do some estimation. Uh, so effective magnetization can be written as the order of E h bar by M R cube, where E h by M R cube is effective magnetic moment of the constituents, where everything else is the effective. This is effective mass, effective size, and E is effective charge. Then, using these estimates, we can further estimate multiple coefficients to be in this form, where you can see that the QLM dash, the magnetic, the induced magnetic, the induced electric multipole due to magnetization becomes much smaller than this part, because MC square is much larger than H, H omega. And for the magnetic multipole, the contribution from both the parts is almost equal. In atoms, the electrons are radiating constituents, so the size of the system can be estimated as of the order of V naught by Z effective, where Z effective is the effective uh, effective charge. And for the above results, using these estimates, we can find the ratio of the magnetic moment, magnetic multiple moment, and electrical multiple moment to be the order of h bar by mcr. And then further uh, writing the value of r to be order of a naught by z effective, we can further simplify it in the order of z effective by 137. And using this, we can find the transition probabilities for multiple moment divided by the electrical moment for the same energies will just be given by this z effective by 137 whole square as the h, as they both have same energy. We can also find transition probabilities for multipoles differing by the one unit, where L is differing by only one part, and this can be found at k square of the order of k square into r square. Where I is the size of the system, k is the wave vector. So for atomic transition, the angular momentum selection permits several multipoles. The lowest multiple dominates. The reason for this is because high angular momentum states get de-excited by a lot of field transition in the atoms. And we can see this experiment that this order is maintained, is of the same order, transition probabilities. For the nuclear transitions, for the high nuclear transition, successive multipoles are not of the same type as suppressed as in atoms. For the lower energy, suppression rate is multiple order is dramatic. So we have to rewrite some of the ratios for the case of the nuclear transitions. The radius can be written as 1.4 into a to the power 1 by 3 into 10 to the power minus 15 meter. So numerically, we can write Kr to be less than h cross omega times a to the power 1 by 3 divided by 140. So estimating the transition probability for the same energies, we can write it in the order of 0.2 times a to the power minus 2 by 3, where a is the atomic number of the system and the probability for the L plus 1 divided by the magnetic multipole can be given by this order, where this order comes from this k square r square, and r is assumed to be 1 point, this 1.4 into a to the power minus 1 by 3 times 10 to the power minus 15, and k square can be written from this part right here. And here we have taken effective magnetization to be dEh bar by Mn, where Mn is the mass of the nucleus by R cube. R is the size of the system, and G is 3 for to account for the magnetic moment of the nucleons. So in the case of the electro atoms, normal atoms, we took effective magnetic moment to be EH bar by MR cube, where we have taken G to be 1. But in this case, G comes out to be 3. Yeah, so that's my part. Thank you.
Uh, Now I'll discuss a tutorial problem. So for the first part, we are given a electrostatic potential on the surface of a sphere represented by phi of r, theta, and phi, and we are supposed to find out what this electrostatic potential would look like for a radius that is more than the for a distance more than the radius of the sphere that is outside the sphere. And for this we have to use the general form of an spherical multipole expansion. So the general form of an exterior spherical multipole expansion can be written as phi of r omega equal to summation over L summation over m ALM over r power L plus 1 into YLM of omega. This is for the distance more than the radius of the sphere, where the coefficient ALM are represented by 4 pi over 2L plus 1 and this integral, uh, which includes the spherical harmonics. So now we know that at the surface, the potential is nothing but phi of r, theta, and phi. So, which can be simply written as r and omega. So phi of r and omega is the summation over L summation over m. The only thing just changes here is the denominator is will be fixed as capital R, which is the radius of the sphere. Now we'll multiply both sides by y star of L dash M dash omega dash, and then integrate over the solid angle omega dash. Uh, so this gives us this equation, which now we know that the spherical harmonics are orthonormal. So the integral ylmn y star L dash M dash d omega would be this combination of two Dirac delta functions, dou of LL dash and dou of MM dash, which is zero if either of L and M is not equal to L dash or M dash, and will be one only if L equal to L dash and M equal to M dash. So this gives us the equation for the coefficient A of Lm as r to the power L plus 1, and this integral of phi y star. Uh, Using substitution in this coefficient A of Lm back to the first equation that we wrote, phi of r omega, we'll get the electromagnetic potential at a distance r greater than r as this term, which summation over L summation over M and an integral. So as for the second part, we are told that the spherical shell has uh, a potential of plus minus V with the sign changing over every alternate octants. So all of its 8 octants will have plus or minus V sign. So, and now we're supposed to use the result that we obtained in part A to find the potential produced by the cell when R tends to infinity. So, as is given in the question that the octants have alternating plus minus V potential. So this implies that the potential sign should change every time phi becomes an integer multiple of pi by 2, which implies that Rm is plus minus 2, which in turn implies that the L is greater than equal to 2, since M can never be more than mod of L. So similarly, the potential also changes its sign every time theta is an integer multiple of pi by 2. Uh, so putting L and M as 2 comma 2 in YLM equation, we get that y2 comma 2 is directly proportional to sine square theta, which won't change its sign when theta is a multiple of pi by 2. It's always positive, never negative, non-zero, always non-zero. So it does not satisfy this requirement. It, so then we'll go one step ahead and we'll try with L equal to 3. So y of 3 comma 2, which is sine square theta cos theta, which is cos theta minus cos 3 theta. So it does satisfy this sign change condition, and it changes its sign every time theta becomes a multiple of pi by 2. So, and for the sake of this asymptotic form where r tends to infinity of the potential, we only need to keep the lowest value of L that is necessary. Uh, so we can say that potential is a linear combination of uh, y3 plus minus n2, where matlab L is 3 and M can be either plus 2 or minus 2. And this potential must be equal to either plus or minus V at r equal to r, small r equal to the radius of the sphere. So substituting this value of L and M back to the phi r equation, we get phi of r equal to V into radius of the sphere divided by distance to the power 4 into a constant, and into the it being a linear combination of y32 and y3 minus 2 is represented by this bracket, which can be further simplified by putting the values of y of 32 and y of 3 minus 2, which will result in a final potential as a function of theta and phi. So this is our final asymptotic potential as r tends to infinity. Uh, with this, we conclude our presentation. Thank you.